Hey everybody, this is Dr. Jacobs. This week we're going to learn about the dependent samples t-test. So let's go ahead and get started. So by the end of this unit, there are several things that I want you to be able to do. First, I want you to be able to explain the differences among the within, between, and matched group research designs. I want you to be able to explain when to use the dependent samples t-test. I want you to be able to determine whether the data meets the assumptions for the dependent samples t-test and if the test is robust to the violation of those assumptions. I want you to be able to find the correct critical values for the dependent samples t-test. I want you to be able to calculate the dependent samples t-test test statistic. I want you to be able to accurately write and interpret the results for the dependent samples t-test. Also, I want you to be able to accurately calculate Cohen's d for the dependent samples t-test. All right, so let's get started. Let's go ahead and review the hypothesis testing steps. This is one of the things that I want you to be able to do by the end of the class. So it's really important that we memorize them now so that we have this as the framework to use for the rest of the semester. So when I ask, like, what is step one, go ahead and answer it out loud, or make sure that you have the answer fully thought out before moving on. So what is our first step? Our first step is to determine which statistical analysis to run. What's step two? Step two, you will write your research and null hypotheses in symbols and in words. What's step three? Step three is checking your assumptions to make sure you can run this analysis. Then what's step four? Step four is calculating that test statistic. What's step five? Step five is calculate, or not calculate, but find your critical values using the T critical value table, at least for this unit. And what's step six? Make a decision. And then our final step. Step seven is conduct any relevant follow-up analyses. All right, so our first step of the hypothesis testing steps is to determine which statistical analysis to use. So for this, we'll ask ourselves a series of questions to determine whether or not we would use a dependent samples t-test to analyze the data for whatever research question that we have. So for this, we'd ask, okay, so what's the purpose of the dependent samples t-test? The purpose of it is to see if there are significant differences between groups. How many samples does the dependent samples t-test examine? And for this one, we also have two. The next question that we ask ourselves, what type of basic research designs does this mean that we're going to use with the dependent samples t-test? And for this one, we use either a within group design or a matched group design. If it's either of those, then we will be doing the dependent samples t-test. So this is what separates whether we're going to use the independent samples t-test versus the dependent samples t-test. And they're really close to one another. So when you're trying to determine, hey, which one will I use? You're literally just going to look at this one here, which type of research design. If you're using a between group design, you'll do the independent samples t-test. If you're using a within group design or a matched group design, then you'll do this dependent samples t-test. What level of measurement is a dependent variable? And on here, it has to be either an interval or ratio level of measurement. We also know that as a scale. All right, so we use a dependent samples t-test when we want to compare two groups that are related to see if there are any significant differences between those groups. So this is what you want to go ahead and put on that statistical analysis sheet that I told you all to start building when we started learning the one sample z-test. So on your list now, you should have one sample z-test, one sample t-test, independent samples t-test, and now dependent samples t-test. Sometimes you'll hear the dependent samples t-test called a paired samples t-test. It's actually exactly the same thing. And if you're using something, some statistical software like SPSS, it actually uses this other name, paired samples t-test, rather than dependent samples. There are two ways that our samples can be related, and we've already kind of talked about this. We're just putting this in different words. If you use a within subjects design, that means you're using the same participants in each of the groups. If you use a match subjects design or a match group design, we are pairing up our participants on some sort of characteristic. You can go back to chapter 1 lecture to review that, or the reading from chapter 1 to be able to figure out what this means. So in order to conduct the statistical analysis, our dependent variable must be on a scale. Okay, so we use the dependent samples t-test when we want to compare two groups that are related to see if there are any significant differences between groups when our dependent variable is on a scale. Okay, so we are going to go ahead and review those basic types of research design again, because it has been a little while. A between group design is when we test different participants in each of the groups so that we can compare the differences between those groups. So for example, if I want to compare the exam scores between my face-to-face statistics course with my online statistics course, I would be looking at the significant differences between two groups that are made up of different participants. And if I were going to do that, the type of analysis we learned last week was the independent samples t-test. Within group design then is when we test the same participants multiple times. So for the dependent samples t-test, we're testing our participants twice. Okay, so an example of this would be a pre-test and post-test given to the same class to determine if there's gains in their learning. And we actually did this in this class. We took a pre-test at the beginning of the semester. In a few weeks, when we come to the end of the semester, we'll also take a post-test. And then I will use this for myself to see how much my class overall learned across the semester. And then you can also do the same for yourself, because I can allow you to see those scores, even though those scores aren't entered exactly into your grade. Those post-test scores will also help you try to see, okay, am I doing pretty good with content, or should I spend a lot more time reviewing some of the concepts from across the semester? So the match group design, this is the trickier one, and we'll have more details on match group design and match subjects design on the next slide. But if we're going to do a small summary, this is when a researcher matches participants on a particular characteristic that may be a confounding variable, and then tries to equally distribute the participants in each group based off of that characteristic. So what this does, this allows groups to be close to equivalence at the start of the study on whatever characteristic that we're doing. So let's do an example. So if I wanted to study the difference on taking an online statistics course versus taking a face-to-face statistics course, there are certain characteristics I might want to try to control for when completing the study. For example, level of intelligence would be something that I would want to account for. So, because if one class had more students with a higher IQ, the differences between my classes may be due to differences in IQ rather than the differences in the method of course delivery. So likely I'd want to use a matched subjects design in a study like this if it was possible. So if I wanted to do this, there's some steps that I would have to follow. First, I'd have to get the IQ scores for all of my participants. Then I would have to put the participants in order from highest to lowest IQ. After that, I would take the two people with the highest IQ scores and randomly assign one of them to group 1, which could be, let's say, my online class, and the other one to group 2, which let's pretend that's my face-to-face course. But we'd repeat this process until all participants have been assigned to one of the groups. So you would randomly assign in groups of 2 where the first participant went, and then the other participant would go into the other group. So this would be a matched subjects design because the groups are related to one another based on IQ scores. All right, so this moves us on to step 2, writing our research in null hypotheses in symbols and in words. So when we do this, when we're writing our hypotheses, the very first thing that we have to do is determine whether we're going to write our hypotheses directionally or if we're going to write them non-directionally. If you write your hypotheses non-directionally, you're going to use the two-tailed test. This is going to sound very familiar. If we write our hypotheses directionally, then we're going to use a one-tailed test. With the dependent samples t-test, it's going to be really, really important that you keep track of which group that you placed first. A lot of times when I'm doing a dependent samples t-test, I like to use the little sub letters to help keep track of which group is which. A lot of times, if I can do this, or if it makes sense, I like to put the group that I'm hypothesizing in my research hypothesis to be larger first, because that helps keep the numbers positive later on when we're calculating our test statistic in step 5. And when I said step 5, I meant step 4. So let's fix that real quick, and I'm gonna go ahead and reshare my slides. Hopefully it's still sharing the correct one. There we go. Yeah. So in step 4, when we calculate our test statistic. All right. So non-directional hypotheses. Remember, whenever we write non-directional hypotheses that we're using two-tailed tests, that means when we go to draw our normal curve later on, that we will have 2 critical values. We'll have a positive and negative critical value, but they'll be the same number. So when we do this, we're going to write H sub 1, which means what? Hopefully you remember that means research hypothesis. Then we're going to put our colon, which means we're about to tell everyone our research hypothesis. With the dependent samples t-test, we're comparing the means of each of our groups. So we're looking at the mean of group 1 does not equal the mean of group 2, because when we write non-directional hypotheses, we're not sure which group would have the higher mean. So now we have a template, research hypothesis template. The mean of group 1 is not equal to the mean of group 2. So if I wanted to write this example out non-directionally, which doesn't make a lot of sense, but if I were to do that, I would have research hypothesis, the mean of the online statistics course pretest is not equal to the mean of the online statistics course post-test. So then after I write my research hypothesis in symbols and in words, then I would put that into, I would go ahead and write our null hypothesis. So we have H sub 0, which is our symbol for null hypothesis. Put a colon, then we have X bar sub 1 equals X bar sub 2, because remember our null hypothesis has to cover everything that our research hypothesis doesn't cover. Okay, so I can give you a template for this. This means null hypothesis template. The mean of group 1 is equal to the mean of group 2. And so we remember, we don't just write out these templates when we're doing these calculation assignments or when we're doing real studies. We take that template and we adapt it to whatever research question we're trying to answer. So if we go back to looking at these online statistics course pre-test and post-test course, we'd have null hypothesis, colon, to tell everyone that our null hypothesis is coming. The mean of the online statistics course pre-test scores is equal to the mean of the online statistics course post-test scores. Okay, so here we can either choose to write our hypotheses non-directionally or directionally. Remember, we want to try to write our hypotheses directionally if possible, because that increases the power of our test, which means we're more likely to reject our null hypothesis if our null hypothesis is false in the overall population. Okay, so again, when writing my research hypothesis, I like to put the group I believe will be greater first if I can. You don't necessarily have to, but this makes it a lot easier when doing these things by hand. All right, so we have H sub 1, which is our symbol for research hypothesis. Then we're putting a colon. Then we have X bar sub 1, so the mean of group 1 is greater than the mean of group 2. So I have another template. I bet you are shocked for our research hypothesis. So our research hypothesis template, the mean of group 1 is significantly greater than the mean of group 2. So if we want to adapt that, we could have research. So if we continue the other example, remembering we only write our hypotheses either non-directionally or we write them directionally. We make that choice. I'm just showing you how we would do this different ways. So we'd have research hypothesis. The mean of the online statistics course post-test scores is significantly greater than the mean of the online statistics pre-test scores. So as a teacher, I am going to hypothesize that your post-test scores are significantly greater than your pre-test scores. If not, then I haven't done my job and there's something that I need to try to finagle or adapt so that you all learn more after taking the class than before you took it. All right, so after we finish writing our research hypothesis, we'll write our null hypothesis in symbols and in words. So our symbol for null hypothesis is H sub 0. We put a colon so people know that our null hypothesis is getting ready to be written. Then we remember that our null hypothesis has to cover every option that our research hypothesis didn't cover. So we use the greater than symbol in the research hypothesis. So in the null hypothesis, we have to use the less than or equal to symbol. And then we have X bar sub 2, so the mean of group 2. So our null hypothesis template, the mean of group 1 is less than or equal to the mean of group 2. And there's a whole bunch of different ways that you could do this. This is just one way that you could write your hypotheses for these. But it's nice to have a template, especially when you're starting out in statistics and research, because it's just, you need practice to be able to do these things. Okay, so null hypothesis, the mean of the online statistics course post-test scores is less than or equal to the mean of the online statistics course pre-test scores. You're going to notice that I kept the groups in the same order. That's particularly important when we're working with the dependent samples t-test, because most of the time we're going to be using a within group design. We're using the same participants twice. And so it can be a little tricky to keep track of our groups if we kind of try to flip them. All right, so our third step is to check our assumptions. And so our assumptions for the dependent samples t-test, we have our dependent variable is measured on a scale. There's independence within groups. Difference scores are free of outliers. The population that we took our sample from is normally distributed. The sample was randomly selected. All right, so let's go through each of these assumptions individually. So our first assumption that I almost always want to check first, because it's a deal breaker, is that our dependent variable is measured on a scale. So this means that our DV has to be on an interval or ratio level of measurement, or we violate this assumption. The dependent samples t-test is not robust to the violation of this assumption. So what that means is if our dependent variable is not on an interval or ratio level of measurement, then we can't do it. We can't move on. We cannot pass go and collect $200. We have to stop, and then we have to figure out what the non-parametric equivalent of this analysis is. All right, so independence within groups. This is all cases within each group are independent of one another. So when we do this, this means that the participants within the group aren't influencing one another's score. So if I had someone in the online class give all the answers to the pre-test and post-test to their peers, or if two people try to take the pre-test and post-test together, which wouldn't make sense because you get participation points for doing it, that would mean that each individual case isn't independent anymore. And that would mean that we violated this assumption. So the dependent samples t-test is not robust to violation of this assumption. Unless we have reason to believe otherwise, we just assume that we meet this assumption. Sometimes there'll be things that happen where it comes to our attention that one participant's data is influencing another. But for this, we just assume that we meet it unless we have reason to believe otherwise. However, if we violate this assumption, then it is not robust to violation of the assumption. So that just means that if these observations are not independent within the group, then we cannot do this analysis. All right, so our next assumption is that our difference scores are free of outliers. And so although we've dealt with outliers before, this one's a little bit different than the way that we've done it. So when we're calculating our dependent samples t-test, we're actually going to calculate something called difference scores. The difference score is literally just the difference between each pair of scores. So what we'll do is we'll have, because we know that each of our samples are dependent upon one another, if we have our participants, so let's say we have participant 1, the difference score would be the difference between their post-test score and their pre-test score. That is a difference score. To test this assumption, then we need to find the z-scores of each of those different scores. So for participant 1, we need to see what the difference between their 2 scores are. Remember, we're going to keep our groups in the same order. We don't switch them so that we have all positives. We keep them in the same order. So if for participant 1, we're saying their post-test, or if we're saying for the whole class that the post-test is significantly greater than the pre-test, that means when we're doing these different scores, we'll have our post-test scores first minus all the pre-test scores. This means that there is a possibility that there will be negative scores. Hopefully there won't be, but sometimes say like if I have a student who didn't do any of the work, but then in the last week wanted to do the post-test, or maybe students didn't watch any of the lectures, or they didn't do all the readings or whatever like that. If students didn't do all the content, it's very likely that they wouldn't gain any additional understanding. So sometimes I will see that happen if I have a student that hasn't been engaged in the online class all semester. So after you get those different scores, then you would calculate the z-scores for each of them, so that we can see. And if we have any different score that has a z-score that is beyond a plus or minus 3.29, then we consider that a significant outlier. So here, if you have a z-score for your different score that's positive 3.29 or above, or negative 3.29 or below, that will be considered an outlier. So if any of your different scores meet that criteria for an outlier, then you violate this assumption. However, the dependent samples t-test is robust to the violation of this assumption if you remove the outliers prior to running the analysis. However, you need to note that if we remove any outliers, that we need to indicate that in the results section of our paper, how many participants that we removed and why. So we never just remove data to remove it. We don't try to change our data anyway. If remember, like when we're doing these, this is typically within the scope of doing research. Typically when we do research, the goal of it is to disseminate our research out into the scientific community, whether that's sending our research studies out to peer-reviewed journal articles. Well, we'll have 3 experts review it and really tell us all the things that we've done wrong. So we have to make things easier on ourselves, so that we tell them, hey, we did this. This is why we did it. So don't question it, basically. And then sometimes we'll disseminate our research at conferences, where if you've ever seen Big Bang Theory, sometimes people are kind of contentious and will argue about your research and things like that. So you have to know what you're doing and why. Okay, so then the next assumption is that our different scores are normally distributed. So this is a different take on something that we've seen previously. So this assumption means that our different scores should be normally distributed. What is one way that you could check that? So there's a couple ways you could check this. One way, you could literally take your different scores and build a histogram to see if it follows kind of the normal distribution shape. The other way that you can do it is we can use the Shapiro-Wilk test for normality to test this assumption again. So if our Shapiro-Wilk test for normality is statistically significant, in other words, our p-value is significantly less or is less than our alpha level, then we violate this assumption. If our p-value is equal to or greater than 0.05, then we meet this assumption and we're good and can move on and check our next assumption. However, if we violate this assumption, we can still do this analysis anyway. So it's robust to this violation as long as our sample size is 30 or bigger. So this is the number of participants, so this would be how many paired scores we have. So we remember that we have a participant 1 gives data for the first group and the second group. So we need 30 participants or greater to go ahead and be able to run this analysis anyway. So testing for normality. The Shapiro-Wilk test actually has its own test statistic symbol. It's W. Test to see if this test tests to see if the distribution of your different scores is significantly different from the normal distribution. So if we want it to be normally distributed, do we want the distribution of our different scores to be significantly different from the normal distribution? Think about it before moving on. No, we do not want them to be significantly different than the normal distribution. This is one of the few times that we don't want significant results, and we see this with some other assumptions as well. That's another way of saying that for a Shapiro-Wilk test, we want our p-value to be equal to or greater than 0.05. All right, so if you see here, I have a screenshot of what it looks like when you print SPSS results. We'll see here, it says test for normality. And then when we're testing for normality, we'll look for the Shapiro-Wilk test information. We'll see a statistic, we'll see our degrees of freedom, and then we'll see SIG period, and that is actually our p-value. So when testing for the Shapiro-Wilk test for this class, I will provide that for you. And then you will just have to look at it and determine whether or not you meet or violate the normality assumption. Okay, so keeping that in mind, if our p-value is 0.445, what is the chance that we'd make a type 1 error if we said there were significant differences? So if we said that our distribution was significantly different from the normal distribution, what would our probability be for that? It would be a 44.5% chance that we made a type 1 error. So again, remember, a type 1 error means that we reject the null hypothesis when the null hypothesis would have been true in the overall population. So for this, what decision would you make for the Shapiro-Wilk test of normality? We would retain the null hypothesis for the Shapiro-Wilk test for normality. In other words, we found non-significant results. So if we're going to put that in normal people speak, our distribution is not significantly different from the normal distribution. So if we got this output from SPSS, would we meet the assumption of normality for our different scores? Yes, we would, because the distribution of the sample was not significantly different from the normal distribution. Okay, so our last assumption that we're going to check for the dependent samples t-test is that the sample was randomly selected from the population of interest. To meet this assumption, it means that you randomly selected your sample from the population you wanted to study. So if we review from week 1, random selection means that every member of the population had an equal chance of being selected into your sample. If you do not randomly select your sample, you violate this assumption. However, the dependent samples t-test is robust to violations of this assumption if we don't take what we find from our sample and try to apply it back to an overall population. You would also put this in the limitation section of the discussion section of your research manuscript. All right, so here we have a table that you can use to review our different assumptions for the dependent samples t-test. We're not going to go back through these because that's what we've done in the previous slides, but it's nice to kind of have a little bit of a summary for the materials. All right, so then step 4, we're going to calculate the test statistic value. First, what we have to do is calculate our different scores. Something that's really interesting, well, not interesting, it's actually frustrating, if I'm going to be honest, is capital italicized D represents our difference score. This is unfortunate because this is actually also the symbol for deviation score that we learned earlier on in the semester when we started learning about standard deviation, variance, and mean absolute deviation. Okay. So the difference score, however, is the difference between each pair of scores. With a within group design, this means you take the difference between the first score and the second score from the same participant. With a matched subject design or a matched group design, this means that you take the difference between the paired scores. So if you remember when we did our example, we had, if we were going to IQ test everyone, all of our participants, and we put them in order from the highest IQ to the lowest IQ. And remember, we took our first participant, our second participant, and we randomly assigned our first participant to either our in-person or online class, and then we put our second participant in the opposite group. Those scores are paired. So whoever they were paired up with their IQ, that's what we would use to find the different scores, remembering that we're keeping the groups in the same order. All right, so our dependent samples t-test formula is a little bit different than what we've seen before. It looks not as scary, but you have to go and find those different scores and then you plug them into this formula. Something that's really important to keep in mind, however, when doing this, is that when we're looking at those parentheses and we're looking at the summation symbol, that we're making sure to do that correctly. So there is a difference between taking the summation of your d-squareds, right, versus finding the summation of your different scores and then squaring it. So those numbers are going to be dramatically different. So it's really important that when we do this, that we're paying attention to what we're doing with those parentheses, especially when the summation symbol's involved. All right, so pro tip, if I have an idea which group is going to be bigger, I would put that first when writing our hypotheses, and especially your research hypothesis, because that's the direction that you're hypothesizing with your test statistic. So for example, if you expect your students' post-test scores to be higher than their pre-test scores, when you're writing your hypotheses in step 2, you're going to want to say that you think the mean post-test scores are going to be significantly greater than the mean pre-test scores for the class. Honestly, it doesn't matter which way you do this, as long as when you're writing your research hypothesis and null hypothesis, you keep them consistent and keep track of the direction that you're doing. All right, so our summation symbol. The statistical analysis sometimes gets a little bit tricky because of the notation with the summation symbol. So note that the summation of d-squared and open parentheses, summation of d's, close parentheses, and then squaring that number, those are different calculations. A summation of d-squared means that you're going to find all your d-squared scores first, and then you're going to add them all together. When we have find your summation or open parentheses, summation symbol d, close parentheses squared, that means you find all the d scores first, the different scores first, then sum them together, then square that number. So let's practice this. So if we look at it, our open parentheses, summation symbol, different score symbol, close parentheses squared. If we do that, we're going to go in and find those different scores, and then we're going to add them up together. We're going to find that sum. Here we see that's 7, and then we're going to square that number, which we find is 49. So then when we're doing the summation of our d-squareds, what we're going to do is find all the different scores squared first. We'll add those up, and then we have our number. So we see here that after we squared our different scores, we had 25 and 4. And then when we add those up together, we had 29. And we see that these are significantly different from one another. We have 49 versus 29. So when you plug those into your formula, you're going to want to make sure that you have the right one. And this is why when we're doing homework for this class, I give you a whole week to do it and keep encouraging you to come into office hours. And it's been really great meeting a lot of you, whether it's been in person or in Google Meets, to be able to work through some of these questions that you're having. That moves us on to step 5. That's finding our critical value or values. To find this, there are 3 things that you need to use the student t-distribution table. This is in last week's folder when we started learning about the independent samples t-test. We have I may have labeled it the t-critical value table. So if you did not print that or you don't have a PDF copy of it, you're going to want to make sure that you save it. To use this, you need to know if it's a 1-tailed or 2-tailed test. You need to know what alpha level we're using. So for this class, we're always going to use 0.05 unless I tell you otherwise. You're going to need to know your degrees of freedom. The way that we calculate this actually changes for a dependent samples t-test. And we'll see that with every statistical analysis that we use. It changes depending on what we're doing. So again, our degrees of freedom, our symbol for that was DF. If that's not on your symbol sheet, you want to make sure that you have all of these symbols on our symbol sheet. And the way that we calculate that changes depending on our analysis. So for the dependent samples t-test, the way that we calculate it is we have n minus 1, where n equals the number of pairs that we have. So we're not talking about necessarily the number of participants. We're looking at the number of pairs. So for within group design, that's just the number of participants. With the match group design, it's the number of paired scores that we have. So this is what our critical value table looks like. And hopefully you have a copy of it. So to use our critical value table, we go to this table. You're going to want to make sure if you've printed it out, or even if you have a PDF, that you annotate it, that you see that it's for t-test. All these tables start to look alike after a while. And so it's really important to make sure that they are being labeled correctly, so it's easy, especially if later on you go on to a different stats class, say like you're going on to grad school or for a master's or PhD or professional school of some sort. This probably won't be the last time that you use statistics, and you're going to want to save these tables because I actually programmed Excel to calculate all these values, to do the calculus to calculate all these values, because what I found is in a lot of different textbooks, they actually had the wrong numbers. So you may want to save these for that purpose. Okay, so first you're going to want to determine your alpha level. Here we know that we're going to use a alpha level of 0.05, so we're going to go to the left side of the table. Then you're going to want to determine whether we're using one-tailed or two-tailed test. Where do we find that again? It's how we wrote our hypotheses. So if we wrote our hypotheses directionally, we're using one-tailed test, and we'll look in that column. If we wrote our hypotheses non-directionally, then we'll look in the two-tailed column. After that, we're going to find whatever our degrees of freedom were for our sample that we used. This says now to determine your alpha level. I'm already going to be looking at that if it's me. And then we'll intersect those to see what our critical value is. So we remember if we're doing a two-tailed test, that it's going to be a positive value and a negative value. If we're doing a one-tailed test, it's going to be however we phrased our research hypothesis. So if we said we thought group 1 would be significantly larger than group 2, then it's going to be a positive critical value. If we said we thought group 1 was going to be significantly less than group 2, then that critical value will be negative. Okay, so step 6 then is making a decision. When we do this, the very first thing I'm going to have you do every time is draw this normal curve out and label it. So in the step, either we reject or retain our null hypothesis. To reject our null hypothesis, the test statistic must exceed the critical value. I didn't say bigger than, I didn't say less than, because that really depends on how you phrased your research question and your research hypothesis. So if our critical values on the right side, because we said group 1 would be significantly larger than group 2, then we want our test statistic to be larger than our critical value. However, if we did a negative critical value, because in our research hypothesis, we said that our group 1 would be significantly smaller than group 2, then that's actually going to be smaller on that side, right? And that's why I like to use the word exceed. It also brings back the language from when we did the area under the curve unit. So if our test statistic fails to cross the critical value boundary, then we're going to retain our null hypothesis. To help make this decision, always just draw out the normal curve when appropriate. And there's going to be only a few situations where we're going to have to adapt how we're doing this, but the process is still going to be basically the same. So in addition to labeling the critical values, our retain the null hypothesis region, our reject the null hypothesis region, and our zero, we also want to label our test statistic value, because that shows us which decision we're going to make. Okay, and in this one, we reject our null hypothesis because our test statistic value exceeded our critical value. So if we're labeling it for a two-tailed test, remember we have two tails on our normal curve. The critical value will be the same number, but one will be positive, the one on the right side, and then one will be negative, which is the one on the left side. So if we're labeling our normal curve for one-tailed test, we remember it depends on how we phrase our research hypothesis. If we believe that in our research hypothesis that the group 1 will be significantly larger than group 2, our critical value will be on the right side of our normal curve, and it will be positive. If in our research hypothesis we believe that group 1 would be significantly less than group 2, then our critical value will be negative and on the left side of our normal curve. So in this step, we can write our results out in words and in symbols. So in words, either you would write retain the null hypothesis or reject the null hypothesis. Those are the only two decisions you can make. But then we can also write them in symbols as well. So when we're reporting our results, it's very similar to what we did so far. And actually, it's going to follow the same pattern. So once you start realizing what this pattern is when writing our results, then it'll be very easy for you to interpret even statistical analyses that you haven't learned to calculate. So here we see that we have T. So that is a symbol for the T test statistic. Remembering T is a type of test statistic. The symbol T does not mean test statistic. All right. So far we've learned a Z test statistic, which would have a Z, a T test statistic, which is a T. So here, whenever we have that symbol, it indicates that we conducted a T test. It doesn't tell us whether we're doing an independent samples T test or a dependent samples T test. It's just saying we use some sort of T test. After that, in parentheses, we have our degrees of freedom. We know that the way that we calculate those are different depending on which statistical analysis that we're doing. Then we have equals, and then this is going to be our test statistic value that we calculated back in step 4. Then we're going to have a comma. We're going to have a p value. We're actually not going to calculate the p-value. Remembering our p-value is the probability of making a type 1 error if we reject our null hypothesis with the t test statistic value that we calculated in step 4. So here we know that p-value is associated with our test statistic and our alpha level is associated with our critical value. And there are two different ways to be able to make the same decision. So if we have our p-value, say like we find that we are going to retain our null hypothesis. If we retain it, here we would put our p-value equals n dot s dot, which stands for not significant. However, if we have significant results, then we'll put our p-value is less than our alpha level. Remembering for this class that we're always going to use 0.05 unless I tell you otherwise. But when you're out in the real world, if you're using alpha level 0.01, then you would put that there. Then we're going to put a comma. If we have statistically significant results, which means we rejected our null hypothesis in step 6 here, we have to move on to step 7 so that we can conduct any relevant follow-up analyses that we might have. And for this one, it's going to be a Cohen's d. Okay, so if we have significant results, we're going to move on to step 7, and we're going to conduct our follow-up analyses. So one way to do this is effect size. Effect size, again, tells us how meaningful our results are. So Cohen's d, to calculate this for a dependent samples t-test, we're going to look at the mean difference score, and then we're going to divide it by the standard deviation of our difference scores. And I got a little ahead of myself. So based off of what we know about our symbol so far, what do you think m sub d represents? I already told you the answer. So you can check if you're paying attention, right? This is the mean of our different scores. And I told you the answer to this next one too, because I got so excited. So this is what does the standard or the, there I go, giving you the answer while I'm asking the question again. See, I hope that your fluency in symbols is so great that if you were teaching this class online, you'd be doing the same thing right now. So what do you think S sub capital D represents? It represents the standard deviation of our difference scores. So to calculate Cohen's d for our dependent samples t-test, you got to calculate the mean of our different scores and the standard deviation of them as well, which is okay because you actually already calculated those earlier on, but to calculate our z scores for each of our different scores. So we had to do that anyway. So with Cohen's d then, we have some interpretation guidelines. Once we get a Cohen's d of 0.20, we can interpret that as a small effect size all the way up till we get a Cohen's d of 0.50. Once it hits 0.50, it becomes a medium effect size. And then we call it a medium effect size until Cohen's d gets to 0.80. And once we get to 0.80, that becomes a large effect size. So this is all that I have for you this week. If you have any questions, please let me know. I know some people were like, hey, can we have some extra homework, some extra things to go through? Remember, within each of these chapters and these really complicated ones, I go through the steps with an example, but I also have some extra resources for that too, where we do an example all the way through. So you can definitely use those, and you can go through the process with those without seeing the answers first. And that's 100% what I would do, is go through and make sure whenever I ask questions within the text that you don't necessarily write it in comments or anything, but you quiz yourself on it so that you make sure that you're understanding information. And as always, I am available in office hours to answer questions if you have them. And I really look forward to meeting all my students, even if they're online. The same type of resources, sorry, I was choking a little bit, are there available to you. So I hope that if you have any questions that you're reaching out. So have a great week, and I'll see you next week.